2023 was the hottest year on record by a large margin. But why does NASA NASA's Goddard Institute for Space Studies, or GISS, creates its global temperature record using land and ocean surface data collected from thousands of instruments and buoys around the world. But this critical data set of Earth's temperature has an origin story that starts 100 million miles away, on planet Venus.
It's 900 degrees hot at the surface, has powerful high-altitude winds, and is blanketed by a dense carbon dioxide atmosphere.
The Goddard Institute for Space Studies here in New York was set up in the early 1960s to provide a connection between NASA and the academic community. And so it was very much an ideas shop, and so we spent a lot of time with the formation of galaxies and black holes and planetary program and Voyager, and we were involved very early on in some of the missions to Venus and Jupiter.
Back then, when GISS researchers were studying the weather on Venus, scientists noticed something fascinating. A thick atmosphere made up of clouds and carbon dioxide was trapping heat. So much heat that Venus had a surface hot enough to melt lead. This trapping of heat is known as the greenhouse gas effect. One of the lead Venus researchers at GISS, Dr. James Hansen, realized that greenhouse gases were also building up in Earth's atmosphere. So he switched his sights to his home planet and pledged to model the changing atmosphere of Earth. And to verify or ground truth his model, he needed real-world measurements over time. So he began keeping track of Earth's global temperature record, dating back to 1880, when there was a sufficient amount of data to pull from.
We used our expertise in understanding literally the clouds of Venus and the clouds and dynamics of Jupiter, and then we took that and we started to think about how you would do the same thing for the Earth.
Since then, GISS has kept its sights on the global temperature record.
And that was the birth of GISS as a climate modeling institution.
And scientists have seen a clear trend in that record, rising temperatures. And they know why.
The key difference between, say, this decade and the decade before and the decade before that is that the temperatures have been rising because of our activities, because of principally the burning of fossil fuel.
Without the presence of humans, Earth's temperature would rise and fall due to a complex array of natural drivers. With human presence, however, the temperature just continues to rise. We know that by observing temperature anomalies. Measuring temperature anomalies means that we look at the change over time rather than absolute temperatures. The data map you see here isn't showing that the Arctic saw warmer temperatures than the tropics. It's saying the Arctic was that much warmer than the Arctic has been in previous years, which is an anomaly in Arctic temperatures. But how do we get those anomaly measurements? Let's say you want to track if apples these days are generally larger, smaller, or the same size as they were 20 years ago. In other words, you want to track the change over time. Imagine each person on your apple measuring team has their own food scale. Person A measures apple 1, and their food scale reads 6 ounces. Person B measures the same apple, but their scale reads 7 ounces. Since these scales are calibrated differently, your team ended up with 2 different recorded weights for the same exact apple. There's some imprecision in the measurements. And to account for that, when you compare this apple's measurement to the apples growing next year, you'll need to look at their difference rather than absolute weights, focusing on the anomaly or how much heavier or lighter the next apple is from year to year. So for temperatures, while it would be great to have the same exact scale or thermometer all over the world measuring the temperature in the same exact way, we don't. Instead, we focus on how much warmer or colder the temperatures are in each place based on their own instruments. Another factor to consider is since you're tracking apples from all over the globe, there are differences in baseline weights. Let's say apples grown in Florida are generally larger than apples grown in Alaska. Like in real life, how Floridian temperatures are generally much higher than Alaskan temperatures. So how do you track the change in apple sizes from apples grown all over the world while still accounting for their different baseline weights? By focusing on the difference within each area rather than the absolute weights. So when it comes to the temperature record, scientists aren't comparing temperatures in Bermuda to temperatures in Greenland and averaging them together for net warming. Instead, they're comparing the change in temperatures in Bermuda to the change in temperatures in Greenland. Again, we look at the anomaly measurements to track the change over time. Now, let's scale this example up.
If you have a weather station that's, say, here in New York City, and you compare it to a weather station in Washington, D.C. or Montreal, they tell very different stories about the absolute temperature, right? So Montreal is colder, Washington, D.C. is often warmer, but when they move up and down, when there's a month that is warmer or colder, it's basically the same in all three locations. And so by looking at the anomalies, how much warmer it is than normal for that particular point, and then you look at those anomalies at all those different points, and you can average those. It turns out that you can fill out the gaps much more effectively.
As you can see, this big picture global temperature is comprised of much smaller concentrated data points from all over the world. So while globally temperatures averaged out to be record hot, it wasn't record hot in every single location around the world. But why did 2023 see record heat? Well, to put it simply, a combination of high greenhouse gas emissions and the transition out of 3 consecutive years of La Niña conditions and into El Niño conditions led to record-breaking heat. But the year was, in some respects, still surprisingly hot, and NASA is continuing its research on why. Typically, the largest cause of short-term, year-to-year differences in temperature is usually La Niña and El Niño weather patterns. La Niña generally cools things down, while El Niño warms them up. The largest cause of long-term, decade-by-decade differences in temperature is greenhouse gas emissions and the subsequent trapped heat by greenhouse gases. So while we don't expect every year to be a new record like 2023, we do expect new records as long as we continue to increase greenhouse gas emissions.
The key thing to take away from all of this is that the long-term trends are pretty much relentlessly up. We're going to continue to have records be broken because that baseline is moving all the time. And then the weather is sitting on top of that. And so when the weather is warmer than normal, then we're going to get these records. But even when it's cooler than normal, we don't go back to what it was.
Hopefully we've answered some of your questions surrounding 2023's noteworthy temperature record. But you might be left wondering what we're doing about it. NASA is your space agency when it comes to powering solutions. We're helping other agencies and groups with efforts to reduce future warming. Clean solar and wind power is being planned using modeling from NASA Goddard's MERA and NASA Langley's POWER. NASA is also developing green aviation that aims to make air travel more sustainable through new flight technology. And we're also helping people adapt to climate change challenges that are already here through programs like OpenET, helping water management across the Western U.S., and Black Marble, which uses nightlight data to provide critical information to first responders after hurricanes and other hazards and disasters.